Yeah, comes on everyone. Let's start off. So last thing that we did was this one. Let's go ahead with more. Hope everyone has resolved the notes. That is important. Like getting it after every class, just go there and just take out the question again and spend some more time and resolve. If you don't do that, the question doesn't become yours. It's like you're just coming to the theater and watching the movie. So if there's something similar comes or something they twist and give, you will not even understand. Like you know what you'll think in the exam. You'll think in the exam, oh, I have seen this somewhere before, but I don't know what to do. Getting it? That happens. That it is like you're meeting your long lost friend. That's it. So that is of no use. You have to solve. Even last year, right, when we did the advanced revision program, now there were I think two questions which came directly. Matlab, because we did so much variety, something popped up. I think one came in heat transfer and one thing. People call me and tell me, sir, remember you told in the revision it came. I said, great. Did you solve the question? No, sir, I didn't remember how to do in the exam. I said, what the hell, matlab? Why are you so happy about it? So do make sure to resolve. Again, I bol raha hu. It is not like you have to cover everything, right? It is not like you have to do all the materials, which is not possible. But whatever you're doing, try to do it properly, right? So keep it simple. Try to do one or two materials maximum and do it thoroughly. Do the class notes, do the revision notes, and do the extra questions I'm sending. That itself should take care most of the chunk, but finish all the LN GRSC sheets and finish all the FitGiga sheets. I think this is a very good amount of work for next 2.5 months or whatever, right? And then keep writing your advanced papers. So let's go ahead. Let's start off with something little easy and then we'll bump up. We got a disk. And again, going through the class notes is important. Sigma R, so it's a uniform charge density. I'm sure you remember this. This point is on the circumference. Find the potential on the circumference and find the self energy of the disk. Hope you remember what is self energy. If you bring all these charges from infinity, and if you assemble this disk, the amount of energy required to construct this disk by bringing individual charges from infinity. And if this disk is hinged at point A, and if it is rotated with omega, find the magnetic field at point A. I'll ask you that later. First, let's get these two. You can jump everywhere. Hope the question is clear. Yeah, someone does remember the result. This is a standard thing. So we have a disk uniformly charged. Sigma is the surface charge density, R is the radius. I don't want at the center. I want on the circumference. Center is easy. Find the potential on the circumference and find the self energy of the disk. So how do we approach this? So we should know this technique here. So listen to this. So about this point here, we will take a thin sector. Now, before that, we need to actually find the potential of a sector. So let's go there. If you have a sector, sigma, radius r, let this angle be theta at a distance x, consider a thin strip. So this itself will be a simpler question of thickness dx. So you're considering a thin dx and this will be x theta. Now, luckily, potential is a scalar quantity. So potential due to this thin sector dv will be k. What is the charge? Sigma, that is charge per unit area, and area will be x theta into dx. By radius will be x. X will cancel. V is equal to integral k sigma theta dx. This limits will go from 0 to r. So the potential at the center of the sector will be k sigma theta r. K is nothing but 1 by 4 pi epsilon, so that is fine. So this is your potential, everyone, due to a sector. So here, when you take this thin slice, isn't this also a sector? So at an angle theta, I'm taking a thin slice of d theta. This radius will be r. From geometry, this is capital R, this is capital R, that is small r. I can use sine rule. That would be, or you can just say this is 90 minus theta. That will be r sine 90 minus theta, r cos theta. So r is equal to 2r cos theta. That is the radius of this thin sector. So due to this thin sector, at this point A, the potential will be, you can see the formula here, k sigma theta r. K sigma theta is the d theta for that sector. R is the radius of the sector, which is smaller. So far clear with me? And this turns out to be k d theta, and smaller is what? 2r cos theta. So you cannot take the sectors from the center here because you're asking at point A. So you are constructing sectors which are increasing in length and which are changing with the radius also. So yeah, you're done. So potential at A, what will be the limits? At this point, theta is 0. If you go up and complete here, theta will be pi. If you go below, theta will be, theta will be 90. Because see, 0, 30, 60, 70, 80, as you get closer and closer, you will get 90 here. So limits will go from 0 to 90 and 0 to minus 90. So limits will be minus 90 to plus 90. K sigma do r cos theta d theta, that is sine theta, that is 2. So that is 4 sigma k r. Sigma is 1 by 4 pi epsilon. So we get sigma r by pi epsilon. That's your potential, everyone. Clear with this? So you should know the sector got derivation, and then we used for this. So this is a very important technique, that you can take elements like this. Clear with this? Then how to find the self energy? Now for the self energy, this is what we do. Assume we have a disk of radius x. You're constructing a full disk. So from infinity, bring a dq charge and place it on the circumference. And increase the thickness by dx. Right? So then dq will be sigma 2 pi x circumference into thickness dx. So you're bringing this much charge from infinity and you're constructing a thin shell, meaning thin ring around it. And as you put more and more charge, eventually this will become a full disk. Make sense? Potential at infinity is 0. Potential on the surface, on the circumference, this is a disk. So be careful with that. Potential just now we derived sigma r by pi epsilon, which is sigma x by pi epsilon. Therefore, the small amount of work done to bring the charge will be dq into potential difference v minus v infinity. So dq is sigma 2 pi x dx, and this is sigma x by pi epsilon. Pi goes off, you end up with sigma by epsilon x square dx. So limits from 0 to r. This is the total work done. Sigma r cubed by 3 epsilon. So this is your self energy. So to construct this disk, this much energy you have to spend in order to make this disk. Clear with this? So using this as a logic, I will leave this as a homework for you. You can try. This is there also there in the class notes also, I guess. But don't see the notes before try and then give it a try. We have a square plate. Sigma. This is O and this is A. A is the corner, O is the center. Side A. Find the potential at A and O. Try this as a homework. Spend some time, put a fight. You have to use this. I think I didn't do it in the class. I just gave this part. VO by VA we did. We didn't actually find the values. Try that as a homework. We can see. If you didn't get it, I'll teach you next class. Clear with this, but think how will you do? You will. This might help you what I taught you. Yeah.
Sir, how did we take the element? I didn't understand.
So we have just. That's what I'm telling you. You guys have to go through the note before coming to the class. You have
Sir,
chosen an element like this.
it's
You're taking
not
a.
it's not a part of the sector. It's a different shape. So how
No,
can
no,
we
no.
consider?
You're taking. It's a d theta is so small. You can almost assume this to be a sector. That is the whole point of integration, right? Right? Think about it. When you take a curve like this, and when I say find area under the curve, what are you doing exactly? You're taking a thin slice here. Didn't you treat this as a triangle? And then you said integral y dx is the area under the curve, right?
Yes.
So same way, so since d theta is very small, you can ignore that and you can treat that like a sector. D theta and r. Okay?
Yes, sir.
Yeah, that works. So check it out. But still, if you're confused, let's see after the class we can discuss. Let's see. No, it's fine. Do ask, do ask. I am just in a hurry. Like there are a lot of concepts. I'm worried like maybe I'll not be able to show you everything. I'll just drop them as a homework. So there, we have a shell, sigma r. This is the center. Find the field at the center. That is easy. Aryan, you got something. Please keep your mics on mute, Aryan Shirotkar. So we have a shell. Sigma is the surface charge density. Find the field at the center. That itself would be a mains question. We have an half shell here, and we have another half shell here. They have a common center. This thing has a charge Q1, R1. This thing has a charge Q2, R2. Since both are positive, they'll repel with each other. Both are half shells. Huh? Hemispherical hollow shells. Find the force between them. That is the actual question. The first one still do it because I want you to know how to choose an element for a hemisphere. It comes a lot. You can do that in pressure. It comes in magnetism. It comes in magnetic movement. It comes in electrostatics. So the Shelka integration is very important. Don't worry about the magnetic field. That I'll teach you in magnetic field. याद था मुझे याद था. But first let's finish with this electro का thing. There are actually three important concepts I want to teach you guys. This is one good thing based on symmetries. Let's find the field due to the center. I should know how to chase the elements, because you know what will happen? Tomorrow someone will come and say like this. The sigma is equal to sigma naught sine theta. Now find the field at the center and you're gone. So if you know how to choose the elements, you're done. Sigma r square. R नहीं आएगा रे आदित्य. Oh, please ask me. I'm going little, I'm telling the questions fast. I'm not writing the whole statement. So in case you didn't understand the question, please don't hesitate to ask. And in case you didn't understand the explanation, I know like some of you maybe didn't know the notes or this thing, ask. If it is too big, then wait after the class. I'm there. We can sit as long as you want. For doubts, not to chit chat. Some of you have that habit. Right, Saish? You got a result. You should put in the chat box here. So let me know that you actually got it. So if you actually answer both the questions, then I might give you an additional question for you secretly. You get secret questions also. Let's see the elements, right, Jainil? K sigma pi square नहीं रहना भैया. Integrations are important, okay? It should be like bread and butter. You should be very comfortable with them. Mains mein you might not have seen anything, but advanced mein it's like you see a hemisphere and you know how to choose an element. एक जगह नहीं, it will come everywhere. We have seen this in modern physics, radiation pressure. We will see this again in electrostatics. Gauss law में आएगा, flux calculation में. You will also see this thing in magnetism, magnetic movement. I can ask you any number of things. I can say there is a hollow shell which is rotating with omega. Find the magnetic field at the center. Done. So you can frame questions. So how do we choose an element? From the center. Again, those who don't know, listen carefully there. At an angle theta, take a thin slice. Okay, these are very thin slices d theta. So that will be r d theta. And now this thing, you make it a circle like this. I hope you guys are able to see that. So when you cut it open, you will see something like this. Imagine like this, okay? Take a watermelon, right? And cut it like this horizontally. You will get a disc. Abhi beech mein se remove the red color part. Then you will be left out with a band like this, isn't it? Are you guys able to visualize? Take a watermelon, cut it horizontally, you'll get a disc. Beech mein remove the red part, you'll be left with a green band. So this is how the element will look. This radius is your r cos theta. This element is your r d theta. Right? And now we are going to use this formula, field on the axial line. And this is your r sine theta. What is the charge on the ring? Charge on the ring will be sigma. The circumference of the ring, if you cut it, it becomes a triangle kind of thing. So this is how it will become. This will become 2 pi r cos theta. And this width will become r d theta. So charge on the ring will be sigma into 2 pi r square cos theta d theta. There. And what is the field on the axial line? K, Q, the distance x by r square plus x square whole power 3 by 2. Right? So here r will be r cos theta because that is the radius of the ring. X will be r sine theta. That is a field due to one ring. And then the field at the center, integrate the whole stuff. Integral limits will go from 0 to 90 because when you're 0, you're taking this ring. As you go up, the rings are getting covered like this. At 90, you're covering the topmost ring. You can do this integration. I will leave it there. You'll end up with sigma by 4 epsilon. Then you get a pretty good result. Should remember that. This r is the radius of the ring. I'll just take it as maybe small r square. This is your x. I hope you are getting which formula I'm using. I'm using this formula, field on the axial line. Clear with this? Don't forget the limits and how to choose an element, because you can ask this in multiple places. What about this question? You have taken two hollow hemispheres, and then how do you do that? Someone did type the answer because this was done in the class notes, so few people know. How do we handle this? I hope the question was clear. Two hollow hemispheres, not full. They have a common center. Two KQ1 Q2 by R square. Let's see. So how do you handle this? This is the thing. If you really get these kind of questions in the exam, this will eat away a lot of time, even if you figure it out. You should have seen this kind of models, right? If you have not seen this kind of models, it becomes really difficult to, suddenly get an idea in the exam. And that's what we are trying to do. We are trying to cover as much as possible different things so that you can hit. So when you get the spheres now, spheres are one of the beautiful shapes. They have very good symmetry. So let's see how it works. So first thing, what you do, let's start with this. You want the force between them. Let the repulsion between them, let the force be F1 and F1. So that is what we are trying to find. That is what you asked. Great. Now, consider you have a full sphere. You have a full sphere. In that full sphere, you keep this half sphere. Now, when you take the full sphere, remember the charge will become 2q1 because the charges are given here q1r1 and q2r2. But tell me one thing, what is the field inside the full sphere? Zero, right? That means the force between this half sphere and that big sphere is zero. The force between them is zero. So can I say that means I will split this system into an half sphere and this half sphere plus this chota thing and this big thing. Can I do this? If I add this plus this, won't I get this shape only? Do you get in the logic? And just now we said this is F1. So if this is F1, and because of this part also must be F1. That means if you keep the sphere half sphere this way, or if you keep the half sphere this way, the answer will remain same. Is that logic making sense? Because the full hemisphere, full sphere is giving you zero, then each half must give you equal and opposite forces. Sure? Then, now let's do the other way around. What if you have the small sphere? Now you take this is full and take this is half. Now remember, this is Q1, this is 2Q2. Okay. Now, like I said, sphere is a very beautiful thing. You can literally, replace this with a point charge, and we can say the force between them can be treated as K Q1 by R1 square into 2Q2. So you can do this only for spheres. You can replace that inner sphere with a point charge at the center. Then the force simply becomes field into charge. So this is the force between the half hemisphere and the full sphere. All clear with this? Again, we're not going to do any integration. That is the whole point. Integration would be a mess. Now I can argue this statement. That means now this guy is nothing but this half sphere and this half sphere, and it's like a lot of pictures, so but listen carefully, and this half sphere and this half sphere. Do you agree with this? This plus this is this, but just now we already proved this is F1, so this is also F1. These two are equal, isn't it? So this must be F1. Sure. And we also proved this and this are same, right? So this is this and this is this. So this is also F1. So 2F1 must be equal to this value here, which is K Q1 2Q2 by R1 square. Therefore, we get F1 is equal to K Q1 Q2 by R1 square. Clear with this? This thing is actually, wait, I did a mistake here. Sorry. This was sigma by 4 epsilon. It's not, I took it as a point. That was a mistake. That was sigma by 4 epsilon. And that was the whole reason I derived sigma by 4 epsilon. I wanted to use this result there. So that was a mistake. Because the field due to hollow hemispherical shell is sigma by 4 epsilon. This is the field due to that Q1. Sigma by 4 epsilon to Q2. Then you can substitute, you'll get the answer from here. Clear with this? There, no integration, nothing. But let's say you don't have this formula here, sigma by 4 epsilon, and you still want to find. Then how will you find? Look at this technique here. So this is the full sphere. I can treat that as a point charge. So this will be 2Q2. So from here, at any point here, the field will be E is equal to K into 2Q2 by R1 square. Take a small area here, dA. So you are considering small area dA. So the force on this will be the electric field into the charge dq. So the pressure is force by area. Force is nothing but field, which is K 2Q2 by R1 square into dq by area. But dq by area is nothing but sigma. K2Q2 sigma by R1 square. This is the pressure acting on the shell. Now, on a shell, if you have constant pressure, if the pressure is same everywhere, we can use something called projected area. If you guys don't know about this, should definitely go to the fluid mechanics notes. I'll show it to you. This is called projected area. Quite important, comes in 6 different chapters. We can simply say force will be pressure into projected area pi r square. You could have done this if you don't know that sigma by 4 epsilon. This is an alternate way to find the force between the big shell and that one. So this is a so you're finding force between these two. Are you clear what I did? I replaced the shell with a point charge. Due to the point charge, I found a force on a small area. That force by area will give you pressure on that particular position. And you'll observe this pressure is constant everywhere on the shell. If the pressure is constant on the shell, then we can use something called projected area, which comes in fluid mechanics. The projected area. You should definitely check it out. Page 42, fluid mechanics. Definitely revise this because I'm going to use this extensively in again fluid mechanics and modern physics. You'll also learn something called projected length later on. So we'll see. But is the idea clear, everyone? And the best part about this question, right? Even if your shells are not exactly like this, but if they're like this, answer remains same. Even if you put them at an angle, answer remains same. Independent of theta. You can prove it. That I'll leave it to you as a homework you can try. You do the same logic. You'll take half piece and then you'll keep playing. Understood what we did? So this is one part of the problem. This is the second part of the problem. Then I said this part is equal to this part, and I said this part is equal to this part. Clear with this? Do check it out. It is also there in the class notes. So this is one. Any confusion? Any doubts on this? Great. Next one. We have a solid sphere, rho, and radius r. Rho is your volume charge density. R is your radius, and this whole thing is plus. Now, since everything is positive charge, they will repel each other. If they're going to repel each other, that means inside there is some kind of a pressure. Find the pressure inside the shell as function of x. Think about this. If you just look at this point here, every charge is pushing it away. So it will generate a pressure on this region. So every region will have some kind of a pressure. So what is the pressure at a distance x from the center? And find force between the two halves, matlab the left half and the right hemisphere. Now, because if I assume there are two parts, the right hemisphere and the left hemisphere are pushing each other because of repulsion. Find force between left and the right hemisphere. Uniformly distributed. Yeah, there is a result on this. But anyway, try to derive. Derive because tomorrow someone will come and say rho is equal to rho naught r. The density is not uniform, and then you won't know what to do the derivation. Do the derivation, even if you know the result. You can actually say, since it is a solid, right? You can also say stress actually, stress, pressure. It's a volume stress basically. It's just what we call as pressure only. The same thing I can do in gravitation. If you have a planet, because gravitation, every force is trying to go inside, the whole planet will try to compress. That creates something called gravitational pressure. So you can play around the same thing with gravitation. And how do you find the force between the left half and the right half? That would be the actual question. And that question, interestingly, you can actually do without this first part. This concept of pressures is important. This you can again do it in gravitation also. I'll show you a question like this in thermodynamics. When a star forms, what is star? Star is a spherical solid sphere made of gas, which has gravitation and also has temperature. So we can say it is an ideal gas, which is in the form of a solid sphere. We can do something like that. So again, how do we choose an element? So here we will choose a thin element here, like this. Can you see how is that shape? A small cube. I'm exaggerating the figure here. There, this is how it looks. What is the field inside the solid sphere? I hope everyone knows the result. The field inside is k q small r by r cube. This can be also written as rho by 3 epsilon r cap, rho r bar. Getting it? Or simply r into r cap. Same thing, rho is q by 4 by 3 pi r cube. So you can write in terms of rho. So this thing will have a charge dq, which is rho. Let this area be a, and let this thickness be dr. So that will be rho into a into dr. That is the charge. So this will experience a force of the electric field into dq. You're experiencing tension T plus dt. You can actually say like this. So this is being pushed down by the pressure, which is P plus dP into area. This is being pushed up by P into dA. So this will give you dP into area is equal to E dq. This is dP. Area, the field is rho r by 3 epsilon, and dq is rho a dr. Area will cancel. dP will be rho by 3 epsilon r square r dr. Now when you take the limits, remember the free ends will always have zero pressure. You cannot have pressure there because there's nothing outside which is pushing you. The free ends will always have zero pressure. That means in this case, the pressure at the center is maximum. Now you might feel like, sir, why is the pressure at the center maximum? Think of like this, the molecules which are there, they're actually having some kind of a bonds, isn't it? So when this molecule repels this molecule, you're pulling with a force F. These two molecules are pulling with this, there is a force F. These three are pulling, there's another force F, F1, F2, F3, and so on. So on this point, all these forces, right, they're actually pulling it outside, isn't it? Because there is some kind of a bonds between them which is keeping them together, but everyone is actually trying to stretch outside. So when you take the limits, dP, limits will go from 0 to x. This will be rho square by 3 epsilon r dr. Limits here have to be careful, r to x, because pressure is 0 when r is equal to capital R. This gives you a pressure rho square 6 epsilon x square minus r square. I messed up a minus sign somewhere, I guess. I need a minus sign somewhere. Maybe I should take this thing as P plus dPa. It's pulling out, that's pushing in PDA.
Yeah, sir, pressure will decrease, right?
वो तो है, ठीक है, एक minus sign ले लेना. Check it out, you get a minus sign and that will take care of it. Actually, I think we should take it as a tension by area or something. ठीक है, but that is the idea there. Clear with the pressure, rho square by 6 epsilon r square minus x square. Yeah, I think, yeah, you got the force also. The idea is important. The same thing you can do in gravitation. Gravitation में क्या हो जाएगा? Gravitation में k is similar to g. So 1 by 4 pi epsilon is equal to g. So 1 by epsilon can be replaced with 4 pi g. So the pressure का formula rho square by 6 epsilon r square minus x square can be written as rho square by 6, 1 by epsilon is 4 pi g. So there's no need to derive again for gravitation. So that will be 2 by 3 pi gravitational constant, rho is the mass density, r square minus x square. This will be your gravitational pressure. Because if you take a planet, every particle on the body is trying to attract it towards the center and everyone is trying to compress the body. So the whole solid sphere is under compression. And this leads to a pressure inside the solid sphere. This is what actually increases the pressure. You must have learned in school, right? The Earth's core has a very high pressure. As you go into the Earth, the pressure increases. Where do you get that pressure from? You're actually getting it from the gravitational pressure. This is your gravitational pressure. So you can do this thing, electron gravity. You can simply replace that 1 by epsilon with 4 pi g and the answers will match up. It works. Clear? Question still not over. They're asking the force between them. Now, one brute force way of doing is this. You take any half hemisphere, consider a thin ring of radius x and dx. So on this thin ring, the pressure we know, this will be pressure into area. That is the force on this ring, which is pressure is rho square by 6 epsilon. So if they ask you as an advanced paragraph, this is what they will do. They'll ask you find the pressure and they'll ask you something like this. And the area of this ring will be 2 pi x dx. But for this, you need to know the pressure. This is the force on that one ring. Then integrate. The force on the half hemisphere is half only, will be rho square by 3 epsilon pi integral r square minus x square x dx. And the limits will go from 0 to r. You can integrate this and end up with an answer. Now we have got it. Rho square by pi r power 4 by 12 epsilon, it seems. That looks right. Are you clear what we did? So when you take that half and half hemisphere, the pressures are pushing both of them. The pressure is pushing, but the pressure is not uniform. Got this? But I didn't teach you this question for this actually. I wanted to show something else. This is all good, great, pressure and everything, but there is something even more interesting in this. But all clear so far? The pressure part is clear. Choosing this element, how did I get that? Is that clear, everyone?
Sir,
So if you see, we did, yeah.
sir, we can understand about gravitational force that because it is directed towards center, core will have
Yeah,
higher pressure. But
yeah.
I didn't understand in this.
No, to logically socho na, if you take a sphere and if you put everywhere positive charge, shouldn't they just fly away?
Ha,
But they're not flying away. That means there is some kind of a glue or something. They're sticking together, right? The ball is trying to expand, no?
yes.
So there is a, instead of saying pressure, you can say there is a stress on the material.
Hmm.
That's what we call, right? On a solid, we call it stress. We don't call it pressure actually. So in a solid, we call it volume stress, but volume stress is same as pressure. Can you think of
Yes.
like that? If you take a rod and if you try to stretch it, there is a tension here, na? So that will lead to stress. Are you able to think in that way? If pressure looks
Yes.
confusing, ऐसा सोचो, volume stress.
Hmm.
Now
Okay.
listen to this thing. This problem you could do it without finding that pressure and everything. This is what I wanted to show you actually. Now if you take the whole sphere, right? Consider any random point here. Let the charge be dq. Now on this random point here, we know the field also, which is rho by 3 epsilon r bar. Agreed? Now, if I ask you to find the force on that whole hemisphere, that will be integral field E into dq. This turns out to be rho by 3 epsilon integral r dq. So far clear? If you see this, doesn't this look like something? If you take position vector r center of mass, that looks like integral r bar dm by integral dm. So this is mass into r center of mass is equal to integral r bar dm. Now mathematically, does Max know the difference between Q and M? Max does not know. So Max will think this thing is looking similar to rho by 3 epsilon. Now what is this thing again? This is MRCOM. So I can replace this with R, center of mass, and Q ka place mein I can take the total charge. This is a charge on the hemisphere. because you're finding for the force on the hemisphere. Make sense? Now, for a hemisphere, where is the center of mass? Remember, this is a solid hemisphere. Anyone remember the results? 3r by 8. So the formula will be rho by 3 epsilon 3r by 8. The charge on the hemisphere is how much? Rho into 2 by 3 pi r cube. 3 will cancel. 2 4 rho square by 12 epsilon pi r power 4. Same answer. Why is this working again? Because the field inside is linear. Whenever you see the forces are linear functions, r power 1, center of mass works. We have seen this in pressure also. Yaad hai? If I take a sheet, the pressure acting on this is P naught plus rho gx. That means the force on the sheet can be written as pressure at the center of mass into area. Any sheet, you can put an half disk. You find the center of mass by pressure into area, you'll get the answers. So you can use center of mass here. Is the idea clear? So this would be your general formula. The force on a body will be rho by 3 epsilon, the center of mass ka position vector, or the distance into the charge of that. Clear? Now, based on this, so if I ask you this question, I have a solid cylinder. Infinite. Uniformly charged solid cylinder. Charge density rho, radius r. So everywhere it is positive. Find force per unit length on one half of the cylinder due to the other half. I wanted to use this logic. Integration will be a mess. You can do it, but उसमें भी pressure निकाल के कर सकते हो. But again, center of mass thing will work. There you have your center of mass, pressure, electrostatics. There you can mix up 2-3 things. I hope the question was clear. This is the formula. I'll keep it there. You can refer if you want. Again, don't blindly write this formula. The formula is E dq. So you need to from there get R dq ka term. So that means first you need to find the field inside the solid hemisphere. I think if you have to write a general formula, no? I'll write there. So if you have any random body here, if this is the center of mass, and let's say the field is in this form, field has to be linear. K into R bar should be linear. Then force on this random shape will be integral E dq, which is K into integral R bar dq. This can be written as K into the center of mass into the charge on the system. That is your general formula. Works only for linear functions. So can you find the field inside the solid sphere? That itself is another result. See, Gauss law, everyone. Consider a small cylinder. These are important. You have done something similar in Ampere's law also, if you remember. Magnetic field inside a solid sphere, hollow sphere. In case you don't know these things properly, please check out our Gauss law notes. We have done this detailedly for hollow, solid, everything. So we will take at a distance x, length L. The field will be radial. So Gauss law, integral E dot dA is equal to Q by epsilon. This will be E into surface area 2 pi XL. Charge enclosed will be rho into, it's a cylinder, pi x square L by epsilon. So we get field is equal to rho x by 2 epsilon there. This is your field. Yeah, वही करना चाहिए, but उसके पहले field तो निकालना पड़ेगा ना. So this is your field. So then you're done, right? Now if you see from the top view, it looks like an half disk. Anyone remembers half disk का center of mass? 4r by 3 pi. 4r by 3 pi. 2r by pi नहीं है. 2r by pi is half ring. So then you're done. So this is equal to integral E dq. You just call it as x bar. So this would be rho by 2 epsilon integral x bar dq. So that is rho by 2 epsilon, the charge on that into center of mass. So that will be rho by 2 epsilon. What is the charge on that half cylinder? Rho into pi r square by 2 into L. That is your charge. And center of mass is 4r by 3 pi. This is your force. You're asking force per unit length, so divide by L, you'll get your answer. The charge on the half cylinder is rho pi r square by 2 because half area into L. Clear with this? So this is one important thing. The force on anything, but works only when the field is linear. That is the thing. So there, that's your center of mass, everyone. Clear with this? Let's see one more. Any doubts on this? Anyone not clear with anything particular? Please ask.
Yeah.
Hi.
Actually, the field is due to the whole cylinder, right?
Mm-hmm.
So, but we are finding one half of the cylinder. So, would it be an incorrect answer? Because
I'm waiting. I was waiting for someone to ask. See, so when you took that whole thing, what you're saying is true. So this whole thing consists of force due to everyone and everyone, right? So you're considering the force on this particle due to all these particles, agreed? But question mein pucha tha force due to the left half and right half. Now, so can I divide this entire force into force due to the left half and force due to the right half? Agreed? This is the particle. But if you take this whole thing as one system, the force between these two will be an internal force, right? When you do the summation of all the forces, what is this force of summation of all these forces? These are all the forces between the particles in the right hemisphere, isn't it?
Yeah.
Won't that turn out to be zero because those forces are all internal for it?
But
isn't it?
won't it have a net resulted because it's half?
नहीं होगा रे गॉड देखो ना ये पार्टिकल में ड्यू टू दिस यू आर फाइंडिंग ऑल द फोर्सेस ये पार्टिकल में यू आर फाइंडिंग ड्यू टू ऑल दिस फोर्सेस सो दिस फोर्स एंड दिस फोर्स विल ऑलवेज कैंसिल आउट ना summation of all the force समझ में आया for example देख I'll show you this is particle 1 में all are let's say pushing who is pushing one? Two is pushing, na? But two may also one is pushing back, na? When I calculate for two ka forces, that pair will always cancel out. So it works. Is that thing clear, everyone? Why we can do that? What he asked? Because in the question it is said, find the force between left half and right half. That means I'm supposed to find the force due to the particles on the left half on this each one and add all of them. But what did I do? When I took the field at this point one due to everyone, isn't it? So that means in that force, actually you have forces due to the left half and forces due to the right half. But luckily, the forces on the right side, they'll become all internal. Is that making sense? So it won't matter, they will cancel out. That's a good point, theoretically you can think of. That's a good one. Then let's see. Oh, no, I know too much electrostatics. Let's go to gravitation. Your favorite satellites. So we have a planet here, mass m, radius r. So from here you projected a particle with speed u, mass m, at an angle theta, where u is equal to root over gm by r, your orbital velocity. Not escape velocity. Escape velocity is root 2 gm by r. Now, when you don't throw, if you had thrown it this way, your life would have been easy. You would have gone in a circle. Agreed? But since you're throwing at an angle, this thing will fly like this and will come back and land somewhere on the planet. Find h max and find the time taken to reach the planet again. So this is A and this is B. So it will land somewhere here. Find h max. The maximum height from the center or maximum distance from the surface. And max height from surface. And find time taken to go from A to B. I hope you guys remember the velocities. If your velocity is less than escape velocity, right, and between the orbital velocity and not perpendicularly, you'll go in an ellipse. It's a bounded orbit. I hope the question was clear. The use of centrum was also today. Think. Do you guys know energy of an elliptical orbit formula? You need that. Energy of an elliptical orbit. That itself is a derivation. In case you don't know, should I'll give you the formula, but you should definitely check it out. We did a very beautiful problem here. We have done this question before. There is the thing. Here, page 67. Find the total energy of the satellite. Do check out this question later on, but this is the result, everyone. For a satellite going in an elliptical orbit, I think I wrote it somewhere here in general results. There. Look at this red box. The total energy of a satellite in an elliptical orbit is minus gm by 2a. 2a is your major axis. You need that result. Right, so I will keep it here. Definitely try this problem. It's a pretty good one. It has 4 parts. And this is another beautiful problem, 17. So you should definitely check out these two. Page 67. Energy of a satellite in elliptical orbit. Is minus GMM by 2a. 2a is your major axis of the ellipse. And I hope you know the time period also. Time period is 2 pi root over GM a power 3 by 2. That's your time period, where again a is the major axis. You can solve. इतना lengthy नहीं है, but yeah, there are a few things you have to see. Get this, it's a good one. This is kind of, your Kepler laws ka related. Quadratic नहीं आएगा रे. You should know little about ellipse also, which you know in max. Yeah, you can conserve momentum and energy also. But maximum height नहीं आएगा रे. Maximum height आएगा maximum height. इसे भी कर सकते हो. Yeah, for maximum height, you can do like this actually. At the maximum height, the velocity will be this way. Yeah, you can conserve energy and momentum. First part आ जाएगा. Right. Time will not come. That is also fine. If you can just get the equations, that will do. You'll get a quadratic now, because see, you need to understand when this is going in ellipse, this is the full ellipse, isn't it? Mathematics does not know that you're colliding with the planet, so it will give you answers from this one and this one, isn't it? At both these positions, the velocity is perpendicular. So that's why you're getting two answers. So the negative you will discard, because Max does not know that you're going to collide with the planet and stop. Yeah, you'll get a quadratic. What about the time? Let's see the first part. So at the H max here, the velocity will be, let's say, V, conservation of angular momentum, conservation of energy. So initial angular momentum will be M, U cos theta, V perpendicular into R is equal to MV. Let this distance be small r. So you can find H max. H max will be R minus H. Or I'll just take that only. MV into, keep it as R only. H max will be small r minus capital R. So we'll get it. So that is equation 1, conservation of angular momentum. Initial energy, half mu square. Gravitational potential energy minus GMM by R is equal to half mv square minus GMM by small r. Get V from here, substitute here, solve, you'll get R ka root. So that would be your H max. Clear with this? Time is interesting. How will you go from the time? Now we need to see a few things here. The velocity, right, is special actually. So when you projected this, can you tell me where is the focus for this ellipse? If you remember Kepler's laws, what is the Kepler's first law? All the planets revolve around the sun with the sun at the one of the foci. Isn't it? So in this case, there is no sun, but Earth is there. So the sun, Earth ka center is one of the focus. So if you actually complete this thing, this would be a full ellipse. If the Earth was a point particle, the planet would have, the particle M would have gone in an elliptical orbit like this. That's your Kepler's first law. Now, if you look at the total energy of the satellite, the total energy will be half mu square minus GMM by R. Be careful, not the total energy of a satellite in circular orbit. This is an elliptical orbit. This must be equal to minus GMM by 2a. but U is given, substitute. You end up with minus gmm by 2r is equal to minus gmm by 2a. We got A is equal to R. This is an important result. So you're saying for the ellipse, the major axis ka length, semi-major axis length is R. But tell me one thing, what is this length? This length is also R, right? Because that is the radius of the orbit. This length is also R. Now you tell me in an ellipse, if this is the focus, this is B, this is A, right? And you're saying this A is also equal to R. Which point will that happen? That happens when this point is your minor axis, isn't it? In an ellipse, when you take the distance from the focus to be equal to the semi-major axis, that is the minor axis ka point, isn't it? Yes or no? Dekho na, you got A is equal to R. So from the focus, this is equal to R means what? So indirectly you're telling me this is point A and this is point B. The line AB is the minor axis. Are you clear with this? That will always be the minor axis independent of theta. Is that clear? So that is your minor axis. So AB will be your minor axis. Perfect. So this was the focus. This is an half ellipse, and this was the another half ellipse. This AB is your minor axis. Great. This thing is projected here. This angle is theta. This is 90 minus theta. So this is theta. And this is radius r. So this is your small thing B, which is your r cos theta. And this is your A. Clear with this? And this value will be how much? A into E, na? Or you can just use Pythagoras theorem there. This will be r sine theta. Done. So what is H max? So you can measure H max from there. And now, how do you find the time period? Remember Kepler's third law? Kepler's second law? The area swept by the radius vector is always equal in equal intervals of time. That means for an area of pi AB, you're going to get a time period T, which is 2 pi root gm into A power 3 by 2. Now, how much area do we have here? So we have an ellipse and we have a triangle. This is the area, no? This area is pi AB, and this will be how much? This is r sine theta. So that is r. So this area will be half into base into, that is 2r cos theta, into height r sine theta. 2 will cancel. That will be r square by 2 sine 2 theta. That's your total area. So pi AB plus r square by 2 sine 2 theta will have how much time? You can use unitary method and finish it off. Are you clear what we did here? So we have extensively used Kepler's laws, the first law and the second law, and the time period, the third law. So we actually used everything. And this works beautifully because the time period, right? The speed is root gm by r. If it is not root gm by r, you won't get this is a minor axis. And then it will become more complex. Clear with this? Think once again. I'll repeat the whole thing, see what I did. So we started like this. You're projecting from here. So this was radius r. When we calculated the energy, we found out that A is equal to r. That means for this ellipse, the major axis is nothing but radius of the planet. So then the question comes, if this was an ellipse and you're saying this length from the focus is the major axis, there is only one place where this can happen if this is a minor axis. I think that you must know. And once you proved that this is the minor axis, I think you're done. This was R and this was R. This was angle theta and this was 90 minus theta. This was theta. You literally got everything. This was 2b. You got b ka value, you got a ka value. You can find area of the whole thing. And the time period should be proportional to the area ka thing. Clear with this? That's how you can play around with the areas there. Take a 5-minute break. Come back in 5 minutes. We'll continue from here. People are exhausted. I also forgot to give the break. Any doubts you can ask. Others go take a break. Get away from the screen for 5 minutes.
Sir, please explain this total energy.
That you have to go to the notes and check. वो formula पता होना चाहिए. It's actually derived here. It's a big derivation.
Yes, sir.
I wrote the page number. You can refer to that. यहाँ पे लिखा. You have the notes, right?
I got it yesterday.
हाँ, once you go to the drive, in the drive में है class notes करके. You can download the whole thing. Page 67. Others go take a break. What are you guys doing, Puraja, Vihan?
Sir, I had a doubt.
हाँ,
वो आपने बोला था ना वो हाफ का किसी का डाउट था कि वो फुल क्यों नहीं आई डोंट अंडरस्टैंड द डाउट
छोड़ देना. If you don't understand, don't bring a new doubt. Let it be.
नहीं नहीं वो
नहीं, don't. I'm telling you ना, don't try to do all these things now. उसका doubt मत लो. तुझे clear है ना? बस keep it simple. वो बस वो ये पूछ रहा था. When we took the electric field, rho by 3 epsilon, that is the field due to all particles.
राइट
But question में पूछा था, find the force between left and right. तो why are you taking all particles?
समझा
Then I said right half में वो सब internal forces हो जाएगा, तो it won't matter. अरे बेहन.
Sir, if it wasn't the minor axis, then can we even solve it? Or
Then I think you guys are pros in ellipse तो कर सकते हो. मैं तो मुझे आए तो I can't do. मतलब तो सोचा अभी ellipse ऐसा कुछ आ गया and ये point आ गया वो ना, something like this. That is not minor axis. So
Okay,
maybe
sir.
I think so you have the data. मतलब पता नहीं how will you do this thing.
ठीक है, sir, homework question.
It becomes more of a max question than physics though. Yeah.
Yes.
This itself is already pushing the boundary.
Yes.
Chalo, come back in 3-4 minutes. Yeah, let's start off. Let's say, do you guys remember this? Parallel plates. This plate has a charge plus Q, this plate has a charge minus 2Q, this plate has a charge 3Q, and this plate has a charge 4Q. Distance between them, this is also A, and let's say this is 2A. Find the charge distribution on the plates, and let me put one more switch here, and this is going to get grounded. So this is the switches. Find the charge distribution before and after closing the switch. When it's a charge distribution, I want the charge on the left. So all the surfaces will have different charges. You can even take area as A. Let the distances be D, D, and 2D. Find charge distributions before and after closing the switch. Find the heat produced when switch is closed. And that will start going into capacitor's का region, but ठीक है. The moment I ask you heat, it becomes capacitor questions now. But you need to do the first one anyway. Now again, by chance anyone has forgotten about the parallel plates, you are not taught this before, you don't have an idea. So you should go to this thing in Gauss law. We have done this in Gauss law only. Again, we did it extensively for parallel plates. You can see same question. I didn't even change the numbers. I just gave it, but the numbers came same. So I think I do remember. You should definitely go through this whole theory of parallel plates. We started from here. Charge distribution on parallel plates. I think it's almost around, yeah, roughly around 15 pages. So page 83, Gauss law. Go through the notes. We have a problem there. There is a recording also. Go through the recording. You will understand most of it. You'll still get confused with something. Yeah, you can ask me next class. But at this point of time, that will be the best. If you can go through the notes and go through the recording, understand, spend some 20 minutes, half an hour. It will take time. Don't try to rush it in 5 minutes. You'll not get anything. When I say go through the notes, read the notes and try to do the problems which I gave in the notes. That will help you. Just don't read like a novel. Find the charge distribution before and after closing the switch and find the heat produced. How do we do this? I'll brief up few things. In parallel plates, right, you have three concepts, I guess, 2 to 3 concepts. The first thing, if you have parallel plates, let's say if you have n plates, and let the charges be Q1, Q2, Qn. Getting it? Here I'm not connecting anyone here, just parallel plates. The total charge outside will be always Q1 plus Q2 plus so on till Qn by 2. That's it, no discussion there. The charges outside will be total charge by 2. Since the each plate ka charge is conserved, how did I get this? You should go to the notes, refer it, we proved it. It will be always by 2. What will be the charge here? This will be, if I take this thing as x, then this charge will be Q1 minus x. This is the first part. The second result, if you have two parallel plates, the facing surfaces will always have equal and opposite charge. If this is plus Q, this has to be minus Q. This also we proved. So this is your second result. This is your first result. Third result, if you have parallel plates and if you connect them with a wire, and if this distance is d1 and if this distance is d2, and if this charge is q1 and this charge is q2, then q1 into d1 will be always equal to q2 into d2. You can do this only for a wire and two plates. This is also, we proved it there. You can check out all that in 15 pages. This is the third result. You will need this thing. I'm going to ask you this again in current electricity. The fourth one, if you have parallel plates, it doesn't matter any number of plates and doesn't matter any number of switches, you do anything. If you ground any one plate, the charges on the outermost surface will always become zero. It doesn't matter what you do. If any plate is grounded, if there are 100 plates and you ground the 51st plate or 43rd plate, if you just ground any one plate, the charge on the outermost will become zero. And don't think it is opposite to one, because whenever you ground a plate, what will happen? Charge is not conserved, isn't it? Charge is not conserved. So this will be the total charge on the plates also. So the charges on the plates will change in such a way that total charge becomes zero. Any plate is grounded, charge on the outermost plates will always become zero. Charge on the outermost surfaces. So these are the four things we proved. If you don't know these things, then it is difficult to solve. First one, the total charge by 2. Second one, the facing plates will always have equal and opposite. Third, Q1 D1 is equal to Q2 D2. Fourth, if you ground any one plate, the outsides will become zero. And the plate which is grounded, charge is not conserved. And you can also prove all the charge from the system will actually flow into the earth. That's where total charge becomes zero. And that's why that total charge outside will be that total by 2 will also be zero. You should definitely spend some time. If anyone has no idea about these parallel plates, no problem. You can spend 1.5 hour. It is worth it. Right? Take your time, do all those problems and check it out for an hour. Once you do it, it's pretty easy. These are the 4 conditions. So then you're done. Then let's see how to do. So first thing, when the switch is open, what is the first condition? What is the total charge outside? Total by 2. What is the total charge? Q minus 2Q, 3Q, 6Q. So Q total by 2. That is 3Q. That is 3Q. This is 3Q. Yeah. Right. Then the problem comes. If this is 3Q, this is not minus 2Q. Why? Because you connected with a wire, charges could have flown between them. So we will start with an assumption. Let this be X. If this is X, this has to be minus X. Remember, just now I told you. Facing plates will always have equal and opposite charge. We are using condition 2. Next condition. X into D must be equal to this into D. So I'll call this Y. So X into D must be equal to Y into D. So basically X is equal to Y. So there. So this also became X. If this is X, this is also minus X. If this is minus X, this should be minus X by 2. Because minus X into D must be minus X by 2 into 2D. If that is minus X by 2, this is X by 2. If you actually know these 4 results, right, the question becomes pretty easy. Like you can just see and start writing everything. You're done. Then if you take the charge on plate 1 and 3 is conserved. Plate 1 plus plate 3, you have a total charge of 4Q, which is 3Q minus X. So 3Q minus X and minus X and minus X by 2. This will give you the value of X. How much is this? Minus 2Q by 5. This is the new charges on the surface. Clear with this? Most of you forgot. There are some new people, they don't know, I can understand. Others, you guys have become gajnis. You guys even didn't bother to open the notes and come. Question अभी तक हुआ नहीं. What happens if I ground the third plate? Now, if you're grounding the third plate, now the story will change. What did I say? If you ground the third plate, outside will become 0. There is no discussion there, right? Outsides will become 0. So what is the charge distribution? Let this be x. This will be minus x. This will be x. This has to be minus x. This has to be minus x by 2. All this thing will still work. Now you cannot conserve charge on 1 plus 3 because it is grounded. Charge is not conserved on plate 1 and 3 because when you ground something, charge can flow to this thing. But you can conserve on 2 and 4. Plate 2 plus plate 4 will be 2q. So that would be 2x plus x by 2 is equal to 2q. We get x is equal to 4q by 5. That's your new charges. Clear this? Like I said, once you know the 4 results, it's pretty easy. The parallel plates, you can do any nonsense, it will come very easily. Question abhi tak hua nahi. How do you find the heat? How do you find the heat? We'll not solve it. I'll just tell you how to handle it. How do you find the heat? Think. I'll give you a minute. See, this is the system before the switch. This is the system after the switch. How do you find the heat from here to here? Something happened and you got heat. How do you think we should approach? Don't worry about solving. Just try to get the approach. Okay, someone did get the answer. Heat also. Initial, final, potential. Yeah, right, Navya. Yeah, right, Shirodkar. So basically, you can treat capacitance का formula कितना था? A epsilon by D. So you can treat this region as one capacitor C, this capacitor C, and this capacitor C by 2. And we can find the energy of the system. Energy of the system का formula क्या था? Q square by 2C. We add up all the energy of a capacitor. So the initial energy of the system will be, we are using Q square by 2C for energy of a capacitor. So that formula will be x square by C, 2C, x square by 2C, x by 2 whole square by 2C. Similarly, I can treat this as capacitor C and C by 2. Find this final energy. The heat produced will be U initial minus U final. Are you clear what we did? If you just look at these two, don't they look like a capacitor ka plates with charge Q and minus Q? So the energy stored in that capacitor is Q by... Now, again, I'll tell you one thing. Most people, when you say we have a capacitor, parallel plates, where is a capacitor exactly? The plates are not the capacitor. The field lines between the capacitor, isn't it? This space, which is filled with the field lines, is called the capacitor. I hope you're getting it. The plates are not the capacitor. Plates are simply the boundary. The region where electric field is stored is called the capacitor. So here the electric field will be between the plates. Clear with this? So that we had to jump into the capacitor for heat, but that is how you do it. So you guys solve it and get the answer, and definitely try to solve it again. You can change the numbers. Like I said, if you do the class notes ka thing, you will find it there. Great. That is one good one. In case you forgot, definitely do that. Let's see one more. We have an infinite conducting plate. And this is grounded. That is a symbol for grounding. Basically, you made the potential 0. You kept a charge plus Q here at a distance D. Now, when you kept this plus Q charge, this will induce some negative charge on the conductor. And the negative charge will attract the conductor. Find the force on the charge Q and find the energy of the system. If you put a charge in front of a conductor, you induce the opposite charge. The opposite charges will attract you. In case you forgot, this concept is called mirror image method. याद आया होगा अभी. Think about it. I'll show you. If you remember, great. If you don't remember, I'll show you one. Get the energy also, Navya. Plate 4 is also earthed. If you the plate 4 also, then khatam ho gaya na. This is 0, so this charge has to be 0. Everything will become 0. Right, Yash? Since there's no potential difference, there cannot be any electric field between them. So there should be no charges between them.
Thank you.
People did get the force. They do remember. How do you get the energy? What is the catch? In case you forgot, like, how do we even do this? You get the name, mirror image method. Let me show you, because if you know, you know. If you don't know, then you're gone. But again, this is slightly out of the portion. So what I think they will do, if at all they give you something like this, they'll give you a paragraph, they'll explain you some concept, and then they'll ask you a question. So imagine if this is a paragraph, this is what I'll explain you. So this is a paragraph, okay? So we have a charge Q and we have a conducting plate, right? So if you actually observe the field lines, now remember, this is grounded. So this potential is 0 and it is equipotential surface. And we know for an equipotential surface, the field lines will be entering the surface perpendicularly. So if you draw the field lines for this plus Q charge, this is how they will look. They'll tell you all the story in the paragraph, maybe. They'll explain you this. Right? And on this side, there are no field lines because it's shielding effect, infinite plate. Now they will tell you, we can compare this. If you take a plus Q charge and if you take a minus Q charge, exactly at the center, isn't this region also potential 0? Because at every point, KQ by R minus KQ by R potential is 0. And if you draw the field lines, don't the field lines exactly look like that, but only the upper half? Is that making sense? The field lines in the upper half for the left and the right, they look identical. Now, can this plus Q tell the difference between a conducting plate and a minus Q charge? It can't tell the difference because the end of the day, force is Q into E. As long as the field is same, you will think, yeah, they are identical systems. So that means you can replace this infinite plate with a point charge minus Q on the other side, just like a mirror image. Are you getting this? That's why this method is called mirror image method. So if you have a plus Q charge at a distance d, this is as good as having a plus Q charge and a minus Q charge at a distance 2d. That's it. So just put a minus Q charge, and what will be the force between them? The force will be minus K Q square by 4d square. That's your force between them. This is the force on the plus Q charge due to the conductor. And what about the energy? This is the catch here. They will explain it till here and they'll leave it to you. And if it is me, what I'll ask you, I'll explain till here, the force part, I'll leave it to you. Then I'll ask you, find the energy of this system. That's the first question in the paragraph. Second question, I will give you something like this. What if you have an infinite two perpendicular plates and this is grounded and we have a plus Q charge at a comma a and this is 0 comma 0. Then I'll ask you the same question, find the force and the energy on this. But how do you find the energy here? So we can replace this thing with minus Q. Great. So what is the potential energy? Minus K Q square by 2D into half. Why half? Because only half of the field lines exist, isn't it? It behaves like that, but in reality, there are no field lines here on the other side, isn't it? And if you guys remember from capacitors, half epsilon E square is the energy density. Energy is nothing but electric field lines. So we take half because only half of the energy is missing. So we take half, since half of the field lines are missing. That is a catch. Sure with this? So we call it a mirror image method. You can simply replace this, and again, इसमें एक important है, it should be grounded. If it is not grounded, you can't do, because if it is grounded, then V will be 0. Then you can compare with this V0, right? If it is not grounded, it can't be done. How will you do for this? So we have two infinite conducting planes. One in XY plane, one in YZ plane. So, and you kept a charge Q at A, comma A. Find the force and the energy of the system. Find the force on the charge and the energy of the system. They'll do something like this. They'll ask you for a single plane, they'll explain you the story, and they'll ask you for this. If half of the field lines are missing, well, because what is force, right, Arush? What is electric field? The number of field lines per unit area, isn't it? So where will you take this thing? You will take this field at the charge, isn't it? Arush, are you there?
Yes, sir, can you please explain it again?
Where are you? You're not there. Okay, your camera is not on. No, wait. Yeah. So I was saying, when you take force is equal to QE, this E is what? Electric field at the charge. Electric field at the position of the charge, isn't it?
Yes.
So now, at that position, there are field lines, right? These field lines are coming from the plate, no? The number of field lines per unit area is the field. Do you get the point?
Yeah.
If
Yes.
I ask you what is the field here, you will take the number of lines per unit area here, no? I don't care what is the field lines here. But when I say find the energy, if you remember the formula for energy density, it is half epsilon E square dV.
Yes.
This E is the electric field in the whole region, isn't it? And dV is the volume in the region. So
Yes.
half of the region does not have field lines, so energy will become half. Make sense?
Okay, sir. Understood.
Yeah. So how will we handle this, everyone? Mirror image method, that is a thing. Don't you guys know how to find images for two perpendicular mirrors? बस वही करना था. That's the reason it's called mirror image method. So anyone figured out what images we'll take? You will go with the same logic. You will say this plus q will create a minus q. This minus q will create a plus q. This plus q will create a minus q. They'll get three images, isn't it? Every time you take an image, you have to alternate the sign, isn't it? So plus q ke image is minus q. Minus q ke image is plus q. Plus q ke image is minus q. If you remember, when you have two perpendicular mirrors, you get two images there. So basically, you can say like this: this plus q is an image due to this guy and this guy ka combination. Then you're done. So these two charges will attract force F, which is kq square by 4a square. These two charges will attract force F, and these two charges will repel, which is kq square by root 2a square. So that is F by 2. Done? By 2 or into 2? Into 2, क्या? kq square by root 2, yeah, 2f आएगा. I'll just write it down. Perfect. So calculate, you'll get the force. Can someone tell me what would be the energy? If you actually draw the field lines now, this is how it will look. The field lines from here, they will look something weird. I'm not drawing properly, but they'll enter perpendicularly like this. So they'll look something weird like this. So 3/4 of the field lines are missing. So this time you will find the total energy of the system and you'll do 1/4. So energy of the system there are 4 combinations. You have to take 4C2. That is 6 elements. So yeah, take the summation of all the energies there. K, Q minus Q by 2A. How many are those? 1 pair, 2 pair, 3 pair, 4 pair. 4 of them. Plus 2 diagonal pairs. K, Q square by root 2A 2 times. This is the total energy of the system. Ka 1/4. Clear this? Q is not on the bisector. You can still do the same thing. You just exactly go to the mirror image method. It works. You'll get the same multiple images. Suppose if the angle is 60, you'll get that 5 images. Got this? And but if they really decided to, why do we take another plus Q? Why won't you take another plus Q? God, this plate ka this is minus Q, right? But this image will again create something here, right? Repulsion. So that also will induce charges on that. Induced charge ka induced charge, right, Aryan? So this plate will get an induced charge. This induced charge will induce a charge. We have to include all that. So we can't do that, but mirror image will give it. So you can try this as a homework. So if they're really in a mood to mess up more, they'll make it even more deadly. We have a center here, and let's say we have a charge Q here. Let this distance be D, and this shell is grounded. So we can also use mirror image method. So we can actually replace this shell with a point charge. Let's see how will you figure it out. I'll just give you an idea. You can replace this shell with a charge somewhere here plus Q at a distance A from here. Find Q and small a. That means this charge Q and this minus Q together, they will create zero potential everywhere on the shell, isn't it? Replace shell with Q and A. Find Q and A. If you can find that, then you'll get the force. This is mirror image method ka little higher version, but yeah. Think of that. But I hope everyone clear with the plates one. Plates is easy. They're like plane mirrors. Let's see one more. We have a charge Q1. We have a charge Q2. So we observe the field lines which are coming from here, they bend away like this. When you extend this angle is 60 degrees, this angle is 30 degrees. So there are a lot of field lines. Among them, this is one field line. See, if the Q2 is not there, the field line would have gone straight, na? Because of Q2, the field line got bent. This is the scenario. Find Q1 by Q2. This is like that hexagon problem we did, remember? Last time I taught you hexagon. Aisa kuch tha. So a field line comes out from Q1 at an angle 60 degrees. And then it bends and goes to infinity. And when you draw a tangent to that, it makes it 30 degrees. So that's your field line. Find the ratio of Q1 by Q2 from this picture. Before this, let me ask you one more. Let's see whether you remember this result. Nere Vihan. If this is a disk, this is a point charge Q. The field lengths are passing through this. Anyone remembers this thing? Flux passing through the disk due to the point charge. This we derived a formula. You can use something called solid angle, but you can actually do this also. This is how we prove this. You should again check out the notes, but I'll give you an idea there. So this disk actually, if you take a sphere, point charge, this is the argument. The flux passing through the disk is equal to the flux passing through this area. The flux passing through this area will be equal to the flux passing through the disk. And this green area is nothing but 2 pi r square 1 minus cos theta. That is the area of that shaded part. That's a pretty good derivation. That acts as the starting thing which we did in calculus. And the flux will divide in the ratio of that. So you should know this result. Quite important. Again, we'll use this in modern physics. Modern physics, the question is this. There's a disk and there's a bulb. The bulb is emitting photons. Find the number of photons hitting the disk. So you can play around like this. So the formula for this is Q by 2 epsilon 1 minus cos theta, where theta is the half angle. This derivation is there in Gauss law. There. This was the question 4, Q by 2 epsilon 1 minus cos theta. I showed it in two ways. I took electric field and I literally integrated this. We got the result. Then we did an alternate method. So page 12, calculus. You need this result. Sorry, Gauss law. So let's assume you know the result. Now try to solve. The flux passing through a disk is Q by 2 epsilon 1 minus cos theta. Without this result, you can't handle that. So if you put a point charge and if there's a disk in front of you, and if the edges are making an angle theta, the flux passing through the disk is Q by 2 epsilon 1 minus cos theta. It's a little exhausting, no? Now imagine 3 hours will be like this. Paper 1. Paper 2 will be even more exhausting. You need to get used to it. So before the session, right, if you're really tired, you had a busy day, maybe take a 10-minute power nap and come to the session. Treat it that way. Don't think like, oh, I'm so exhausted, I'm not absorbing. You can't give this, excuse in the PA, paper 1 and paper 2. Paper 2, you will be exhausted. Doubt ही नहीं है. Not only you, everyone will be exhausted. So what are you going to do about it? Do you have a plan to handle that? Or you're just going to come in that day, give an excuse like, oh, I got so exhausted, that's why I couldn't give. People tell, I do a lot of silly mistakes. They're not silly mistakes. You need to figure out what kind of mistakes you're doing and need to work on them. If someone is doing a lot of calculation mistakes, then you have to become more aware. Like the moment you're doing calculations, slow down. Let it be 30 seconds more, but slow down a bit. Tell yourself, boss, I keep telling you, right? My favorite mistake is this. 3 into 3 is 6. I don't know why. I do this every time. In 11th and 12th, it's a very common mistake. Finally, I did in my advanced paper, chemistry paper mein karke aaya maine. There are certain things. So after that, right, the moment I used to see 3, I used to get scared. I used to have a feeling, oh, kuch to aane wala hai. So you have to be aware. So, yeah. From my side, one suggestion, see, if you're writing a paper, after solving, let's say the answer is there. You got answer A and that answer is matching. Chup chap mark karke aage chale jao. Don't doubt yourself. Getting it? I have seen that people, they start doubting themselves. See, if you have not guessed the question, if you solve the question with your, question with your knowledge, you should trust yourself and go ahead. You should do this with your practice papers right now. If you do that, then you will get confidence for the final exam. So how do we handle this? So listen. Now, by symmetry, there will be also one more field line here, 60 degrees. That also will go here and bend something like this. This also will make 30 degrees. Agreed? Now, if you take a disk here very close, can I say every field line that enters this disk, that has to be in this region only? All these field lines will bend, na? Because if you take Q1, Q2, somewhere in the middle you have a null point, right? The field lines, not that way. Think of this way, sorry. Every field line that goes here, this has to be here only. That is fine. So all the flux that is going outside, that has to be same. How much flux is this? So the flux passing through the disk will be Q1 by 2 epsilon 1 minus cos 60. That is Q1 by 4 pi epsilon. So if this flux is Q1 by 4 epsilon, then flux on this side will be 3Q1 by 4 epsilon. Make sense? So all the lines which are going here, that flux has to be 3Q1 by 4 epsilon, because that one Q1 charge will give you a flux of Q1 by epsilon. All clear with me? Then we will make an argument. If someone is standing at infinity, and if you ask him, boss, what do you see? What will he say? He will say, I don't know all these things. He will simply say, there is a charge here, which is Q1 plus Q2. And he will say, these lines are coming from Q1 plus Q2, and this angle is 30. Is that making sense? So the person from infinity will think all these lines are actually coming from Q1 plus Q2. And how much is this flux? So this guy at infinity will think the flux is coming from Q1 plus Q2 by 2 epsilon 1 minus cos 30. Make sense? But aren't all these field lines that he's seeing, right, same as these black lines? So this flux and this flux must be same. Sure, because the end of the day, this field line belongs to this Q1 only, right? Those lines are only bending. You're not creating any new lines. So if you equate this both the fluxes, so how much is this? So Q1 plus Q2, 2 epsilon 1 minus cos 30 must be equal to 3Q1 by 4 epsilon. Yeah, numbers are not great, but yeah, you'll get the ratio Q1 by Q2 from here. Cos 30 is root 3 by 2. You won't get good numbers, you'll get in roots. But did you get the idea that, didn't we do something like that in that hexagon also? The guy at the infinity thought the charge was 6Q at the center. So the guy at infinity will think the total charge is Q1 plus Q2. And this charge is giving lines of 30 degrees ka angle pe. So he will think all these field lines are actually coming from Q1 plus Q2. Is this clear, everyone? There's one really good question in Gauss law. You should definitely refer to this. This question, not this one. I think let's do that one question. We have a conductor. We have a cavity. This is a conductor with a cavity. If I charge Q1 at the center, let's call this thing center C1 and this is center C2. There's a charge Q2 here, and let's say this distance is D. The radius of this sphere is R. The radius of this sphere is small r. Yeah. There is a point A here on the edge here, and there is a point here B. This is Y. This distance is Z. Okay, perfect. Find the potential at A and B. Due to the charges on the conductor, not the total potential. Did you get the question? This is the solid conductor, a solid sphere. So you actually can't see the cavity. I'm just showing you there. Find the potential at A and B due to the charges on the conductor, not the all charges. There are only 2 point charges, Q2 and Q1. Start with A. Let's try to find the potential at A. First of all, understand like how will the charges distribute. Start from there. Gauss law, right? The headache with the Gauss law chapter is that it's all theoretical. Because of that you have to make statements and prove things. How will the charges distribute? See. I'll put everything, then we'll see one at a time. First, let's do to this guy. This is Q1. Because it is exactly on the center, it will have uniform charge distribution here. Minus Q1. This charge will go outside. That is also uniform because outside is, we are not talking about Q2 interference. If only Q1 was there, this would have been the situation. This is Q1. Perfect. Now this Q2, which is there, it will not keep quiet. This will induce a non-uniform charge. Minus Q, how much? I don't know. You can't find this charge. And because it has to keep that thing neutral, it will induce plus Q. So that means if you look at this conductor, when I say the charges on the conductor, this is what I'm asking. There is one uniform distribution charge inside, which is minus Q1. And outside there is a uniform Q1 and there is a non-uniform charge also. So net charge is Q1 only. But yeah, it's messed up. You have a uniform plus a non-uniform. So I want you to find the potential due to this on A and B. You're getting what I'm asking? These charges. So due to these charges, find the potential. That is the meaning of find the potential due to the charges on the conductor. You can find C. Don't find at A. We can do some argument. What are the charges? This is Q1 minus Q1. Outside you have Q1. This is Q2. We have minus Q and plus Q, right? These are all the charges. Perfect. Let's start with the center. Now let's find the potential at the center due to all charges. Everyone that is present in the space. Okay. This distance is D. K Q2 by D. Perfect. Due to this guy, K Q1 by R. This is due to the outer surface. Plus K Q minus Q by R. Luckily, this is 0. The induced charges will give you 0. This is that induced charges. So this is anyway gone. Then plus K Q1 by, I don't know whatever is this distance, but this Q and minus Q1 both together will give you 0. If I call it KQ1 by some, whatever is that, C1, C2, minus KQ1 by C1, C2, this is basically cavity, right? I hope you know shielding effect. The charges inside the cavity will not interact with anyone outside. So those two will not do anything. Even if these charges were non-uniform, it would have been gone, right? So they will cancel again. This is also 0. So what did you find? You found velocity potential at the center is K Q2 by D plus K Q1 by R. Agreed? This is the total potential at the center of the conductor due to everyone. Since everything is a conductor, can I say VA is equal to VC? Because conductor is equipotential. That means I know the total potential at A due to all charges. Are you clear with this? Then you're done. So you just want to find at A, right? So the total potential due to all charges is nothing but the potential due to conductor plus potential due to the Q2 and the potential due to Q1. How much is this? I know this already. How much? KQ2 by D plus KQ1 by R. Potential on A due to conductor, that's what we are trying to find. And what is the potential due to Q2? This distance is given. Kitna tha? Z. That is KQ2 by Z. And this potential also I know. That is also given. How much? Smaller. KQ1 by smaller. Got it? Clear with this? How to find the potential at B? Now for B, this is the logic. You can't actually use all this method. It won't work because it is shielded inside. I think you can actually find this thing, total potential at B, I guess. Can't find potential to conductor. And find potential at B. This is what we argue. The field inside is only due to the Q1 charge. The field inside will be KQ by Y square. So potential difference VB minus VA is equal to minus integral KQ by Y square dy. Limits will go from, what is the distance given? Y to small r. Are you getting what I did? Because of shielding effect, the outside charges will not affect the field inside. This is the field inside the shell. That is a field inside the cavity. So that field is responsible for finding potential difference between point B and point A. So that's how you find for B. Anyways, make sure to go through this last thing. Last one is little heavy. It's a good one,
This
but
will be R2 by.
सही है, Y to R. Yeah. Clear? So that's a bit about it. We did some around 17 models, but we covered a lot different things. Do check it out. I'll be sending you some additional questions also, which we couldn't have done maybe. But anyway, the important thing, make sure to try these things. And there is a lot of things you have to revise from the notes. That's what I keep telling you. Your notes where you have around 1200, 1300 questions. That itself is your huge collection of questions. If you do that, and if you solve papers and you do the questions in the revision thing, yeah, that should still take care of many things. Okay, with that, we'll wrap up for the day. So I'll see you guys again on Friday. So Friday, we are starting off with rotation. So yeah, any doubts, anything else, stay back, or else you're free to leave. I'll see you guys on Friday, same time.
Sir,